All right, good morning. How's everyone doing? Good, good. I had to do a classroom observation for Izad's class this morning, so I had to go to class at 8 o'clock this morning, and wow, that was hard. I got a lot of respect for people who can get up and go to class or teach class at 8 in the morning. And I think at least some years I saw some math courses that were being taught at 7, which is even more extreme. Yeah, so I feel pretty lucky teaching at 10. All right. So there was a question. Actually, my worst as an undergrad, I had a Saturday morning class at 8:30, and that was pretty harsh. So there was a question in chat about how do we assign an incrementing value to an associative array. So when you've broken up your phrase and you've saved it in your index, how do we increment that? And it's pretty straightforward. So let's do line. Let's just have a line here, which is you know, something that you parsed from a phrase. And let me turn on my screen share. There we go. So let's have a line which is presumably a phrase that you've pulled out of the input. And let me just make my associative array, which I'm going to call hash. And let's suppose this has already been initialized. So hash bracket. Right, now you wouldn't actually set it equal to 1, but assuming that, you know, we've been doing some processing, well, let's say it's equal to 3, right? So echo $, curly bracket, hash bracket, quote, string line, right? We can see a value of 3. How do you increment that? So I would just do it in pieces, right? So so you've got this new phrase, you want to increment it in the hash, okay? Read, modify, write. So first, read the current count out of the hash. Count equals $, curly bracket, hash bracket, quote, string line. And then increment it the usual way. And then hash bracket, this thing equals $count. And now if we look at the value of that tally inside the hash, right, that should be a 4. So just do it like you would any other arithmetic operation, but do it in pieces. Don't try to get fancy and say $, curly, hash bracket, $, plus plus inside parentheses or things like that. You can make that work, but you've got to be careful with it. $, paren changes things that contain $signs inside them, and so on and so forth. So yeah, but you can do that if you like. But yeah, this is basically, you know, read the current count, modify the current count, write back the count. Right, so and you can put echoes, you know, after each of these. I'll put the value of count here, and then here, and then here, and make sure that, you know, you're reading the count, incrementing, and so on. And if line equals, you know, some phrase that we haven't already seen, do the same thing. Pull the count out from there, right? Increment it, and then save it back in there. And if you look at the value that's saved now, it's a 1, because that's the first time we saw the phrase, right? Why did that work? Because, you know, if this is a phrase we've never seen and we set count equal to the value stored with that, it's just an empty thing, right? But if you have an empty string and you add 1 to it, that empty string is treated like a 0, so this gives you a 1. Yes, so empty is equal to 1. Effectively, I mean, it's not, but when you do this kind of expression, it has to, you know, deal with numbers, and it interprets an empty string as a 0. So we're kind of cheating there. The more proper way to do this would be something like this, right? And then if right, and then you're not relying on that fact, or you know, set it equal to 0, or you know, if it's equal to nothing, then set count equal to 1, else set count equal to count plus 1, or whatever your favorite logic structure is for that. So this is the super uber lazy way of just letting the blank be treated like a 0, but that seems to work. All right, and then there was a question, is there an example program that we can experiment with for homework 8? What do you mean by an example program? So an example executable program you can run? No, because if I wrote that in Bash, you'd be able to read the source code. But there's those 5 test files with, you know, input and output that you get from running a correct test program, and so you can use those to test the behavior of your code, and that should also help you verify your understanding of what it should be doing, how it should be breaking up phrases, and so on. And then just, you know, while you're debugging, if you're not ready for those tests on the Linux server, just, you know, write a few phrases separated by periods or, you know, on separate lines and see if that works. And you know, there's different ways to do this, right? That should give you 3 phrases, each occurring once, right? And then, you know, put some duplicates in and make sure that it does the tally correctly. And then you know, start mixing it up. Throw some spaces in the beginning, throw in some multi-line phrases, and then, you know, start joining some stuff together. And throw in some multiple punctuation, and keep making it harder and harder for your program to cleanse and parse the input, right? Until you get to where, you know, your test cases seem to be working, and then try the 5 test cases that are on the server. So that would be a suggestion for kind of creeping up to the solution. All right, good. Other questions? Let's see. If I want to check if I've ever seen a phrase, would you check for a value of 0 or check if the variable is empty? So you can do it exactly like this. If you pull count out of the hash, right, this will tell you if the thing that got pulled out was just an empty line. And since you know you're always storing numbers in there, right, the only time you're going to get something that's not a number is if you never put something into there to begin with. So this is a safe way to see if your phrase that you pulled out here was new. And if it was, then, you know, set the count to 1. Otherwise, count as a number, increment it, and set the count equal to that. Yeah, so since the program's always reading from standard in, if you want to test against those test files, you just do main /temp/homework, you know, whatever. So just redirect standard in. right? And you're redirecting, right? If you did this, you would be trying to read a command line argument, which is not what your program is supposed to do. It always reads from standard in. But any program that's reading from standard in, if we say less than, some file name, it'll read from that file instead. So just redirect standard in. All right. And by the way, I don't know if I mentioned it or not, but really nice job on homework 7 and on the presentations. Those were awesome. Everybody got good implementations of their appointment calendar program, and the presentations were fun to watch, and lots of good work and lots of good creativity there. So really nice work on that assignment. And I'm hoping everybody's going to get 100% on homework 8, because if you get 100 on this assignment, it's really easy to grade. So do it for me, man. But seriously, if you're not feeling like you're heading towards 100% or something really close to 100%, definitely come talk to me. I got 2 hours of office hours tonight, starting at 5. And you can come in, you can show me your code, you can run through your code, we can see what it's doing. I can give you some tests to try, and we can work out whatever issues there are in your version of this script. So definitely come by. Let's make sure your code's going to work perfectly. And really, I'm unless I see something that strikes me as really suspicious, I'm going to grade this by running those 5 test files, right? And then looking to make sure there's comments and things like that. But really, you should be able to predict what your grade's going to be using that grading rubric. So if you're not going to get 100, you should be able to see that before you turn it in. And, if you do that today, hopefully come to office hours and say, hey, test 3 is not giving me the right output. It's adding an extra space on this phrase. I have no idea why. That's absolutely something we can sit down and we can run through your code. I can say, do a bash-x, or I can say put an echo in here. Let's see what this variable is equal to, and we can figure it out from there. So take advantage of that, right? All right, other questions? All right, well, let's talk about processes. I'm just going to stick to my machine here for the time being. So I'm running a Linux system. Okay, it's Ubuntu. It's on my laptop's hardware. It's a Linux operating system. So mostly when we interact with Linux, we're talking about bash. I'm sitting here at a prompt and I can type in, a command, and some response happens. This is a program called bash. It's a C program. You can download the source code of it if you like. You can look at it. You can change it and recompile it. But it's one program. Okay, it's one program out of 327 things that are running on my CPU right now. Okay, there's 327 tasks out there on my machine. My machine's been up for, well, just a day. Bash is one of those, and for the most part, that's all we care about, right? We just see, here's a command prompt, and I want to edit a file, so I'll just say vi file name, and I'll change to this window, and I'll start typing, and so on. Mostly, we just have this very narrow view of our computer, which is, the shell that we're using to interact with typically the file system, right? So modifying files, running files, things like that. But that's one process out of hundreds of processes that are running on this system. Um, and so, in the earlier days of computers did one thing at a time. Um, you didn't have hundreds of things running simultaneously. You had a batch-oriented system where you would take your program, typically on a deck of cards, and you would run it into the system, and something would compile it and execute it, and when it finished executing, um, it would be ready for the next deck of cards, right? And everything happened sort of sequentially. Um, this was even before DOS, actually. This is like 60s era, before DOS, even before QDOS. Do you know what DOS stands for, actually, though? QDOS was a rebranded uh, operating system that Bill Gates bought from a developer in Washington, who had made an operating system called QDOS, and they needed an OS. IBM had gone to the developer of CPM, who decided to go out for a joyride in his private plane instead of meeting with the team of lawyers from IBM. And so IBM came back to Bill Gates and said, "Can you do software for us?" So he bought an operating system called QDOS, and he just called it DOS. QDOS stood for Quick and Dirty Operating System. So technically, DOS is the dirty operating system, which I think is kind of cool. But yeah, the official rebrand was Disk Operating System, but the original genesis of that name was Quick and Dirty Operating System. And Windows, for a long time, at least to me, felt like it was really just a graphical wrapper around DOS. So yeah, all this stuff was running on the dirty operating system. So yeah, machines basically did one thing at a time. And so now on a Linux system, we have all of these things happening. Okay, so what's happening? I can type something like PS. PS lets me look at processes. Okay, and if I type PS, I get 2 lines of output. Okay, I have a first line which says bash, and very little information on here. The command name is bash. The time that it's taken is basically 0, because bash doesn't take a lot of resources. TTY is where it's running. Well, all of this is running on, my one laptop. I don't have a physical terminal, in the other room connected to this. So this is a PTS. That's a pseudo terminal. And it's pseudo terminal 2. And PID is just a number that you can use to identify this process. It's like a student ID, right? There might be lots of bashes, but there's only one process, 26492. All right. There was a second process listed, which was, guess what? PS. That was the command I was executing. Also had taken no time, sitting at this pseudo terminal and process ID 28462. All right. If I execute PS again, I see again 2 processes, bash and PS. Bash is still process ID 26492, but PS has a different process ID, 28466. It's a different process from 28642. And if I do PS again, I get 28474. So each time I say PS, there's a process out there executing the command PS but has a different process ID. Every time I type a command in bash, a new process is created. That process executes my command, and then that process goes away. Now, when I say PS with no arguments, it shows me processes that I have sitting right here in this terminal session. So there's a number of things we can do, and some of these we've talked about, some of these I've used but not talked about, and some of them we've neither used nor talked about. So I'm just going to list some of these things, and we'll dig into details of them. But one thing is to say command with an ampersand at the end to do what's called running it in the background. So this is run in the background. And I'm going to use that to make our analysis of PS a little more interesting. So there's a sleep command, right? If I just say sleep 3, it'll just hang out for 3 seconds before it exits. So I'm going to say, you know, sleep for 1,000 seconds in the background. Okay. And when I do this command with an ampersand, I get a message back which shows me a number in brackets followed by what looks like a process ID. Now if I say PS, I see there's 3 processes now. There's my original bash. There's this new command sleep with a process ID 28933. That's what I got back when I said sleep. And there's my good old PS command, which is already gone, right? But was running while PS was running. If I do a PS-L, I can get more information. And if I do PS-F, that's what I was looking for, I can see the actual command that was run. So I can see there's a sleep 1000 out there. I can see that my bash command is actually run with the command /bin/bash, right? Because bash is a file located in the bin directory. And here's my PS command, which was actually PS-F. And there's a little more information in here. There's a start time. So bash started at 9:59, right before class started. And sleep was executed a minute ago, and my PS-F was executed right now at 10:22. And the user ID, that's the person who owns the process, and this is normally a number, but it's translated into a name for you. If you look in /etc/password, you can see a list of users on the system. You can do this on the Linux server. It's a readable file by the world. And if I look for Nick, I can see my user ID is 1000. If this process had been executed by whoopsie, then the process ID would have been owned by user 112. All right, so it translates these user IDs into names for us. So here's the more interesting part of the output: PID and PPID. So PID is the process ID. PPID is the parent's process ID. All right. So what does this mean? Well, let's look at this line bash or sleep. Okay. Sleep has its own process ID 28933. The parent process ID is what? 26492. That's the ID of my bash process. And the PS-F command has the same parent process ID. That's the ID of the bash process also. So what we have is bin bash, which was process ID 26492, and that created a pair of additional processes, which was sleep and PS, each with their own process ID. Right, so something like that. Now the PS has already gone away, because once it finishes showing you what processes are out there, the command exits. But sleep is still hanging out there running, and my bash shell is of course still sitting out there running. And the parent of my bash ID, my bash process, is 26487. All right, so there's very few versions of PS that I know. There's just PS by itself. There's PS-ELF, which shows everything. There's the PS-U, followed by a username, which shows you processes for that user. So I want to look at PS-ELF, and I'm going to take the output of that, and I'm going to search for this parent process ID 26487. And I see 3 lines of output. All right. Well, one line of output is right here because I was searching for 26487. And so that showed up not as a process or a parent process, but as just part of the command I was looking for. So I'm not interested in that one. Here's my original /bin/bash, right? Which is, you know, the same thing I've been seeing, parent process ID 26487. Here's the line for process 26487. It's a program called console. Okay, that's the terminal program that I run in Linux when I want to open an interactive session. I do a Control-Alt-T, I get a new console window. And the parent of that is 6925. So let's repeat this and let's look for any process that mentions 6925. And, well, we got a bunch of things now. 6925 itself is a process called xfsettingsd. All right. A program that ends with a D is probably what we call a daemon. It's probably something that hangs out as long as the system is up and running, and it listens to requests and responds to them. It's like a server, basically. And that is the parent of a number of processes, including 2 console sessions, the one that we're sitting in right now, right, which is 26487, and another console session which is running on another window, which is where I'm running my program that's you know, taking attendance snapshots and posting timestamps to the video and all that kind of stuff. An app finder, which is a stray thing that I opened and forgot to close, and my browser, which is Google Chrome, and my email client, which is Thunderbird, and that's it. And the parent of this xfsettingsd is process ID 1, and I'm just going to put PSELF into more because most of the stuff at the top is going to be owned by process 1. Sorry, by process 2. Process 1 is called a init. It's the first process that runs when a system boots, when a Linux system boots, and it basically creates all the other processes, except that because I'm running Xubuntu, etc., so the parent of all my processes is mostly 2, right? So all of these system processes have a parent ID of 2. And then all of these processes are started by a init. So there's a whole bunch of those, and some of them are system operations owned by root, and a lot of them are things owned by me. So all of this stuff. Someone said, what happens if we kill it? If we kill that daemon, I think it will shut down my system, which I would normally do in class, except that I'm recording it and I'm zooming. And I think it would kill what's called my X session, and that would bring things to a grinding halt. But you can try it on your own system. You can kill a init if you want, and that changes the level at which the system is running. So I don't know if I went away there or not, but what I did was Control-Alt-F1, which brings me to a different console window. I did go away? Okay, well then I can't demonstrate that. But if you got a Linux system, do Control-Alt-F1, and what you'll see, well, let me just do. All right. Well, I was going to take a screenshot for you, but I can't because I'm in a different realm at that point. Anyway, go to your favorite Unix system, do a Control-Alt-F1, and you'll get to a separate login window that is a non-GUI version of Linux, right? It's the version of Linux that first boots up before all of the X services start. So yeah, that's hard to demonstrate with Zoom. Yeah, since separate realms can be a drag. All right, so let's go back to PS -F. So this information is available, right? Process ID and parent process ID. Now if I do a ps-u nick, I get a lot more information. Let me do a full, right? There's all these processes associated with the user ID nick. They're not all associated with my current interactive session though, and if I just say ps dash f, right, that's just showing me the processes associated with my current bash environment. But if I look for all processes on the system owned by user nick, there's a whole lot more of them, right? There's actually there's 100 plus. And this is because, you know, I'm logged in to my Linux system, and so there's you know, window managers running and mail clients and you know, other things going. Zoom should be in here somewhere, and so on and so forth. So all these things happening simultaneously, right? So a useful command to know is top. Top will show you a quick view of the top resource consumers on the system, the top CPU usage. And you can see GUVC view, that's the program that's running my document camera. And that's a big CPU hog. And then Xorg is my window manager, so that's the thing that's giving me a graphical environment. Simple Screen Recorder is the program that's recording all of this so I can post it. Zoom is, you know, Zoom. Chrome is my Google browser. And those 5 processes are taking a lot of my CPU time, over 300%. Now I have 4 cores on here, so I can go up to 400% CPU usage. But you know, a good chunk of that's being consumed by these things that run throughout lecture. So what else does top show you? It shows you current time, shows you how long the system's been up. So I rebooted a few days ago because my camera was being weird. How many users there are. Load average we've mentioned before. This is a measure of how heavily bogged down your CPU is. You'd like these numbers to be under 1. But you know, when I'm doing stuff like Zoom and 2 cameras and all that stuff, having a number around 3 means the system's working pretty hard, but it's not overloaded. If this gets up to like 6 or 7 or 10, I'm going to be slowing down. I'm going to see, you know, noticeable delays when I try to do stuff. 333 tasks, 1 running, most of them sleeping. Okay, occasionally 2 of them running, but for the most part, my tasks are sleeping, which means they're waiting for something to happen. None of them stopped, none of them zombied. Zombies are a thing, so a zombie happens when you kill a process, but it doesn't die. And so when you kill a process, there's certain cleanup that happens before the process goes away completely. Well, sometimes things happen which prevent that cleanup from taking place. And so the process has been killed, but it hasn't gone away yet, so it's called a zombie. And there's a status column here, this S. S is sleeping, R is running. If you have a zombie, it'll show up as a Z. So that's the thing. What is I? I don't know what I is. And I don't know what KWorker does either. I don't know. We'll make something up. We'll call it intermediate or something. Or irresponsible. I don't know. I'll check that out. Let's see. Mostly this KWorker process and a few processes with way too long commands on them. KWorkers, SCSI drivers. Oh, idle. I like that. Yeah, I think that makes sense. And I don't know what the difference is between idle and sleeping. I gonna guess it's a different state of sleeping. Um, and most operating systems, you're gonna find most processes are sleeping, right, or maybe idle, whatever that is, most of the time. So there's a process that's responsible for dealing with incoming network traffic, right? So it can farm it out to whatever process is looking for it. Googled it. Awesome, nice work. Mostly, you don't have programs that say things like, did you move the mouse yet? Did you move the mouse yet? How about now? Did you move the mouse? Right? You could write a program that checks the mouse position, compares it to the previous mouse position, and if it's the same, doesn't do anything, just goes and checks the mouse again and waits until the mouse is moved. You never want to write a program like that, right? On any kind of reasonable operating system. That's really CPU intensive. So all sorts of things, keyboard events, mouse events, network packet arrival, things like that, they're all event-based, right? You basically tell the operating system, hey, let me know when the mouse moves. And then you go to sleep. And when the mouse moves, the operating system notices it. It gets basically an interrupt. And it says, okay, who wanted to know about mouse movement? You, and you. And it sends a message to each of them, basically wakes them up. And then they can go off and say, oh, where's the new mouse position? So most things, in most operating systems are event-driven. And so you see these processes just kind of hanging out in the background, waiting for stuff to happen. So that's why most of these are sleeping. All right, we've still got some. Oh, my sleep finished. Okay, I was about to mess around with that. So let's throw some processes back here. All right, I got a bunch of processes hanging out right now in the background sleeping. They're not taking any resources. Right, I probably won't ever even see them show up on my top command. They're basically in a paused state. Right, so they're not going to be getting in the way. Now, what we can do is I can kill my bash session 26492. Let me make another window. I can kill 26492, and that doesn't do anything. All right. So there's this command called kill. It's a Linux command. It's also a function that you can call in C. And it doesn't necessarily kill a process. What it really does is send a signal to a process. It sends a message to a process, which says something like, would you like to kill yourself? But it doesn't actually kill it. Okay. And there's different messages that we can send to a process. So there's a sig hup. That's a hang up. So imagine you're connected to a computer with a telephone, and you want to just end the call. You hang up the phone. That's the effect of sending a sig hup message. And processes had certain things they would do in that case. Sig int is what happens when you hit a control C. It's an interrupt. Sig quit is a different kind of termination of a process. It's a quit. And there's different versions like this. Now 9 is a sig kill. That's the hard kill. That one will actually terminate the process. But most of these signals can be caught by a process and managed. We'll talk about how to do that in bash tomorrow. But we can, for example, say I want to trap a sig int, and now when someone's running my script, if they hit control C, it does not terminate my bash script. Instead, it does something else. But signal 9 cannot be caught. If you kill a process with a 9, it's going to kill it. We'll kill our bash session with a 9 in a second. There's some user-defined signals that are free for whatever you want to use them for, sig user 1 and sig user 2. There's alarms we can use, which are related to timing events usually. There's a terminate. There's, where's the really fun one to talk about in here? There's an FPE. So sig FPE is a floating point exception. And if you're running a C program and you divide by 0, did you ever wonder how it comes up with this thing that says, you know, divide by 0? Does it check every time you do a division to see if the denominator is 0? No. It takes your arithmetic and it throws it to, you know, typically a piece of hardware called a floating point unit. And if the floating point unit discovers that it's being asked to divide by 0, it sends a signal to the process, which is a sig FPE. And then the process can decide what to do with that. And typically a process will print out an error message saying floating point exception, and then it will just exit. But it's just another signal. So let's take out our bash process. Let's do a kill-9 on 26492. Let me do a ps-f first from this other window. Alright, so that's what things look like. So let's do a kill-9 26492. And it tells me, you know, warning, program bin bash crashed. And, you know, I can type, but it's not doing anything. Alright, so let's go back over here and let's look at our PS process again. And look at what happened. These processes have a different parent process ID. They were orphaned and they got adopted by a init. Right? They were orphaned because their parent process, bash, got killed. And so now they're owned by a init. They no longer have a pseudo terminal associated with them. Right, and they're still sleeping. I don't know what's going on with this one. Oh, that's not this. This is the 10-minute attendance snapshot program that's running in another window that wakes up every 10 minutes and takes a snapshot of the participant list. So that's what that is. So these were the sleeps that we started from the bash process, and bash went away, and so these got inherited by a init. And a init will let them run out the rest of their sleep, and then they'll exit normally. Yeah, that switch on PS is always a little funky to type. And yeah, I mean, this is a very deliberate language. Parents and you know, killing processes and zombie processes and all that. You know, it's very deliberately derived from you know, the real world. So yeah, that's how you can think of processes. So this one is you know, completely hosed, and I'll just close out that window later. All right, so let's go back to, so you know, nothing happening associated with this particular window. So let's go back and put a process in the background. So I've got a process back here. All right, so some other things that you can do. If you say jobs, you can see all the jobs that you have access to that are sitting in the background. All right, so you know, I have a sleep command in the background. It's running even though it's sleeping, right? It's actively doing whatever it's supposed to be doing. And I can bring this into the foreground with an FG command. So if I say FG %1, it's as if I had not put that ampersand at the end. It's as if I had just said sleep 1000. And if I control C that, it gets interrupted and it's gone. So if I do another sleep 1000, right, whatever I type here is going to be ignored because I'm running this sleep command. If I want to get back control, I can hit a control Z. Okay, so remember, control C, that interrupts your process. That basically terminates it in most cases. A control Z does not. If I do a PS, I still have my sleep process sitting out here in the background. but it's listed as stopped. And if I say jobs, it's stopped. So even after 1,000 seconds have passed, this will not go away. Okay, it's kind of in a paused state. Now, if I want to let it continue in the foreground, I can say foreground and bring it back into the foreground. So that undoes the Control Z. And again, you know, it's ignoring what I'm typing because it's a sleep command. But if I Control Z, right, it's hanging out there stopped, I can put it into the background with a BG command. And now it's running in the background. And if I do jobs, I can see I've got one running job. And so if you put an ampersand after a command, it throws it in the background immediately and leaves it in a running state. So if I want to bring that first sleep command into the foreground, I can say foreground %1. Now it's as if I typed that at my keyboard without an ampersand. And then if I control C that terminates that process. But my other sleep command is still hanging out there. And if I look at jobs, I can see that. So the main takeaways are, you know, command with an ampersand, Control Z, background, foreground, %number, jobs. And you don't really need this %number. You can just say foreground and it will do the most recently backgrounded process. Yeah. And then you know, all the variants of PS. So PS, ELF, PS, PSF, PSU, followed by a name. The other one that's fun to play with is PS-AUXF. And if you do this, you get a nice little hierarchical description of your processes. So it shows you, you know, here's K-thread. All of these processes are children of K-thread. And here's a niche. And then here's some other processes. Here's AHI daemon. That's resolving .local domain names on my system. And here's a process that was created from that process. So you can see sort of the inheritance or the lineage of processes. And somewhere in here should be all of my stuff. Well, so here's all the stuff coming off of Chrome. Yeah, so here's my interactive session, and here's all the processes running up underneath that. There's Thunderbird, there's Chrome, and Chrome you can see spawns a whole bunch of processes. Right? And there's my app finder. Okay, so I ran screen recorder by using app finder, and there's my console session, which is running bash, and my timestamper. And here's another one running the snapshotter, which is doing that sleep 600. And then here's the console session we're sitting at right now. All right, so that's a little bit of the high-level view of looking at processes. So so tomorrow I want to look at signaling and using the kill command to send signals and trapping signals and responding to those. And then I want to look at how this happens in C. How do we actually create processes? How do we signal processes? How do we connect processes together with pipes and things like that? So, so we'll play around with that next. All right, thanks. Have a good one. I will see you next time.